animal types, but in the planet there are a few hundreds of animals. So if I want to perform a classification task for hundreds of animal types, then the number of classes will be increasing, and also there will be several pairs of classes which are similar to one another, right? And the classification task becomes more complex, and that's where we need more and more complex models. As you would have been already told, one of the most successful models for image classification has been the convolutional neural networks, which have been mainly developed for dealing with what are called the different types of variations that occur in the image data, right? As indicated here, typically the image contains the variation due to translation, scaling, skewing, and maybe other forms of the distortions. What do you mean by the translation? As we have seen, the particular image is supposed to have the animal, but if you take two different images, the animal will not be present exactly in the same location. Even if the same animal is present, it will not be present exactly in the same part of the image. So these are what are called the translation variations. Then we have the scale variations, where the size of the animal will be different from one example to another example. And skewing is the orientation in which the animal's part is present in the given image, right? So these are all the natural variations that occur. If I ask you to write a character in a small grid, right? If I ask all the people in the audience here to write, right? None of the characters will match. No two characters will match exactly, right? Even if I ask you to write the same character, right? No two characters that people write, right? Or even if the same person writes the same character, right? They'll not be exactly the same, right? So there will be translation variations, there will be scale variations, there will be skew variations, right? So how do you make this classification model robust to this kind of variations that naturally occur in the images has been what has been addressed in the design of the convolutional neural network models. Before this convolutional neural models were kind of invented, people are using the standard multi-layer feed-forward neural network model, where we typically have an input layer, then we have one or more hidden layers and an output layer. And all the nodes in one layer are connected to the nodes in the next layer. That's why we call it as a feed-forward neural network. And what each of the neurons in the first hidden layer is doing is it's taking the inputs from all the nodes in the input layer and then extracting some new features, right? And when you're talking about images, if I feed an image into the model, then we are extracting what are called the global features from the image. And typically the global features are not necessarily the good enough to perform many of the complex classification tasks. So basically the conventional neural networks are designed to extract what are called the local features, where we focus on only part of the input at a time and then process that part and then extract a feature. And like that, we extract multiple features. So basically, the convolutional neural networks are designed to extract local features and multiple local features. Because we've already gone through this detail, right? I'll just only summarize what this model is. So this is what is called one of the first convolutional neural network models, which was designed for handwritten character recognition. So basically, we give the image where a character is written, and then we have what we call the convolutional layer here, where there are different feature maps. Each feature map consists of some number of neurons, where each neuron takes the input from one part of the image. This is what is called the receptive field of this neuron. And typically, we apply what is called a kernel function on the receptive field, and then process the content of that receptive field to extract a feature by the neuron in the one feature map here. And typically, the weights for all the neurons in one feature map are same, so that all the neurons extract the same feature, but from the different parts of the image. But extracting one new feature is not enough. We have to extract multiple new features. That's why we have several convolutional and several feature maps, right? Where each of the character recognition for the English alphabet, where there are 26 alphabet letters. So we have 26 plus here. That's why it's called layer. It's not 26 nodes. Okay. And because we are extracting the local features from the input images, right? Even there are all these variations like what we talked about, translational, scaling, and skewing, right? The feature extraction makes it more robust to deal with all these variations. That's why this model has been one of the most successful models for performing image classification tasks, particularly complex tasks. And over the past 15 years, there are several deep convolutional neural models that have been developed. And one of them is what's called this VGG-net, which stands for the Visual Geometry Group. And all of these deep CNN models have been trained on what is called the ImageNet dataset, which is a benchmark dataset. It has got the data of 1,000 different classes, and many of these classes are very close to one another. And I think the number of examples runs to a few billions. Okay, and there have been a lot of benchmark evaluations that have been done on this ImageNet dataset. And what you can see here is again the white colored blocks here are the conventional layers, and the blue colored ones are what we call the pooling layers. And finally, before the output layer here, where there are 1,000 nodes corresponding to 1,000 classes, we have what are called the fully connected layers. And that's when actually this new type of activation function called the rectilinear unit has been introduced. Before that, people have been generally using what are called the sigmoidal activation functions like logistic sigmoid or the tanh sigmoid, right? But it has been shown that this ReLU activation function is very effective when you are getting this image data, and this is one of the most common used activation functions in the convolutional network. And over the years, several types of this deep CNN models have been explored. Actually, there is a nice survey paper which talks about the different deep CNN models for the image classification and their performance on this ImageNet dataset. And it tells how good are these models, right, in performing this 1,000 class classification task. Okay. And there are many other tasks in the image domain people may be interested in. Okay, it's not just the classification task. Another task of interest is what's called the segmentation of an image into regions of interest, right? Like in this case, suppose I have this image. Now I want to segment the part of this image where only the cat is present. All right. Or I have here another image where I have different objects of interest here, like persons and an animal and so on, right? And I want to identify the different parts of this image correspond to the different objects of interest, right? So there is another kind of CNN model which is called as the unit, mainly because the objects of that model is in the form of the U, right? But it's basically convolutional layers and the pooling layers combinations of them, right? And this is one of the most commonly used model for the segmentation task. If you're just interested in only the segmentation task, right, then one typically uses this unit model. And there are also other types of models which are used not only for segmentation but also to detect the objects that are given in the that are present in the given image. Again, one of the most commonly used or explored models is what is called the Foster region-based convolutional neural network, shortly called as the Foster RCNN. As shown in this example, it not only tells where the different objects of interest are there, it also identifies what that object is, right? In this case, it tells where all the persons are there, where the cycles are there, and so on, right? So basically, this model has been kind of designed and then trained to perform not only the segmentation, but also identify the objects of interest, right, in the given image. But it also uses mainly the principles of the convolutional neural network and the variations. Okay. So after successfully solving many of these classification tasks and segmentation tasks, in the past 7 to 8 years, people have been looking at how to solve more complex problems. What we can involve in training a neural network model, whether it's a CNN model or any other model, we typically have training examples, right? Where, let's say if it's a classification task, we have the input image and we know what is the class label for that, right? And we use this information to train a model. This is what is basically called as the supervised learning, right? But here we're talking about only the images and the class label information being used to perform the training of the model. Now, I want to go for a more challenging task. Given the image, I want to come up with a sentence that describes the content of the image. Like when you read the textbook or papers, there are figures and the tables. And for each and every figure and table, you also have what is called a caption, which explains briefly the content of that figure or the table. Right? What is the purpose of that? You know what you're going to get from the content of that figure or the table, right? It's mainly to aid that process, right? So here our task is, given an image, how to generate a sentence that describes the content of the image. Obviously, it's a much more challenging task than a classification task, right? Because what do you need in order to perform this task? You need to identify what are all the different objects of interest that are present in the task and the image, right? Then you need to semantically link the different objects, then form a sentence in a particular language, which is syntactically valid, and it's also meaningful, okay? Now, let's say I show this image and then ask the humans to give the captions, and I collect the training examples. Now, can we build a system which can be trained using this data? What is the training data now? Images and the captions given by the humans for these images, right? And what kind of a model can do this task? If I use only the CNN model, it can only perform the classification, right? It cannot generate a sentence, right? So we also need a model which can generate a sentence, right? That's what we are going to look at. And as you can see here in the bottom example, instead of just looking at the complete content of the image, I can try to identify the different objects of interest first, right? And then link to these objects in order to come up with the sentence, right? Like it says here, there's a woman here, there's a camera here, there's a crowd here, right? So we identify all these entities in the given image and then form a sentence saying that a woman putting a camera in crowd. Actually, one can make use of all these segmentation models or the object detection models, right? In order to perform its task to get the content of the image. But once you get the content of the image, how to form a sentence is one of the most challenging tasks that people have addressed over the time. And one of the successful paradigms for this image captioning task is what is known as the encoder-decoder paradigm. Of course, this comes in many other topics as well, right? So what this paradigm for the image captioning task involves is that we use a CNN model as an encoder, right? Which takes an image and then generates what is called a representation of the image, content of the image. As we're seeing, the CNN itself can be used as a representation generator, right? And once we get the representation of the image, then we give that as input to a recurrent neural network model, which can be trained to generate the text, okay? Because, I mean, you might have studied the recurrent neural network models as the sequence classification models. Like if I have a sentence and I want to identify the sentiment associated with the sentence, right? Typically, I can go for a recurrent neural network. But here, I'm going to use the recurrent neural network as a generative model where I want the model to generate a sentence based on the content of the image that's generated by this CNN. As you already have been told, the standard feed-forward neural network has this kind of a structure, but the recurrent neural network, we have connections from the output of the hidden layer back to the hidden layer. That's why it's not a feed-forward neural network, right? There is a feedback coming from the output of the hidden layer back to the input of the hidden layer. That's why it's called a recurrent neural network. And this recurrent neural network has the ability to deal with the sequence classification tasks as well as the sequence generation tasks. And the early recurrent neural networks have been built using the basic neurons, which are based on the sigmoidal activation functions, but it has problems like what is known as the vanishing and explosion rate problem, mainly for the complex tasks. And that has been kind of handled or addressed by using what is known as a long short-term memory cell, which forms basically a neuron, and it has got the three different gates like the input gate, forget gate, and output gate. And this forget mechanism basically enables it to perform this sequence classification task or a sequence generation task in a better way, and it avoids this launching delay problem, and it also leads to faster convergence for training the model. So more or less, the current recurrent neural models are all based on the long short-term memory. So basically, we explore the image captioning task now, where we use the CNN model and a recurrent neural model in the form of an LSTM, right? So now I give the image as input to the CNN model, but I take out the final layer here, because final layer is required for the classification. So we take the output of the pre-final layer of the CNN model, which is supposed to contain the representation of the image. Now that goes as input to the hidden layer of this recurrent neural network in the form of the LSTM. And what we do in this LSTM model to generate sentence is that based on the input from the CNN model that contains the representation of the image, we generate the first word, right? Then the representation of this first word goes back as input to the hidden layer, and then it will try to predict the second word. And this process continues until we reach the end of the sequence. So basically, we have a model here which can generate a sentence, and we have another model here which can take the image and then get the content of that image as a representation. So now I use my training examples, which are in the form of images and the captions, right, to train the whole system here. After the system is trained, then I give a new image and I expect the system to generate a caption for that image. Okay, so that's how this combination of CNN model and the LSTM model have been explored for performing this image captioning task. And an extension of this is what is known as the dense captioning task, where I want to generate a caption by first generating the partial caption for the different parts of the image, right? Like in this case, let's say there are three different regions of interest, okay? And for each of these regions of interest, I'll come up with a kind of a phrase, like in this case, for this green colored region, I'll say it's a girl playing with, and the orange colored one, black tennis racket, and this blue colored one, it's an yellow spotted ball, okay? And then we need to link these three and then say, right, a girl is playing a yellow spotted ball with the black tennis racket, okay? So instead of doing this caption generation in one shot, right, we split that task, right? Identify the different regions of interest, like using the unit or the first of CNN, and then use those regions of interest in order to generate these partial captions, and then put these partial captions together to generate a caption for the whole image, right? And whenever we do that, we refer to it as the dense image captioning. And there is also what is called the image paragraph captioning, where we may not generate just one sentence, but we'll generate multiple sentences, right, which forms a paragraph. And all these multiple sentences in the form of a paragraph give a very detailed description of the content of the image. Okay, I'll show you some examples later. Then, whatever we're doing for the images, I can also do it for the video data, right? Now, instead of an image, if I have a video, how to come up with a caption that describes the content of the video, right? And typically, video consists of several frames, and there are several events that occur in the video. Okay, so typically, the dense video captioning involves these multiple stages. First, we do what is called the event proposals. Basically, we identify the different parts of the video where each part of the video is associated with an event. Then we try to come up with a caption for that event, and then we put all those generated captions for different events to generate the detailed caption for the complete video. So basically, we have the event detection, then the event description, then combining these captions for the different events to generate the caption for the whole video. I'm not sure whether you can read here. These are parts of the video that have been shown here. And for the first part, there is one sentence here. For the second part of the video, there is another sentence here, and so on. Now, we have multiple sentences that are used to describe the different events in the video. And then we put all these sentences put together to form a detailed caption for the whole video. This is what's called the dense video captioning. What kind of structure you would need for this? Again, you need to have a module that identifies the events, right? Then you need to have a module that generates a caption for each of these events. Then you need one more module that puts all these generated captions together to form the dense video caption system. Okay. So far we looked at how to come up with the system that can describe the content of an image or a video. Now we'll go into a more complex task. Okay. Now we'll get into what are known as the question answering tasks, especially the visual question answering tasks. Textual question answering is very common, right? Whenever you write the exams, right, you are given a question, then you are asked to give an answer, right? It can be a multiple choice type answer, or it can be a one word answer or a detailed answer, right? That's called the textual question answering. Now, what is visual question answering? Given an image or video, and if I ask a question related to the content of the image or video, I want the system to come up with an answer for that question, right? Like a simple example here, I have this image here, and I ask the question, is there something to do that the vegetables fit? All right? Now I want the system to come up with an answer as yes for the first image here and no for the bottom image. All right? How do you build a system now? What does that involve? Yeah.
Firstly, the image needs to be captioned in a latent space, let's say.
Right.
And that needs to be passed as the context
right.
for the question.
Right.
Now, the language model will use both the question and the context to give the answer.
Correct. Right. So basically, you need to have a module that will capture the content of the image. Then you need another module that processes the question, right? And then you need to relate both of these in order to come up with the answer, right? Now the answers can be multiple choice type question answers to make the task simpler, or you can have it as an open question answering type, right? Where you not give multiple options, you want a system to generate the answers. Okay, so both these kinds of systems are being explored. So the other examples here are like given this kind of images, and the question is who is wearing glasses, right? The answer in this case is man, and the answer in this case is woman, right? And for these images, if I have the question like how many children are in the bed, the answer should be 2 here, and the answer should be 1 here, right? So all of this requires some kind of understanding the content of the image, right? Understanding the question, then relating the question to the content of the image, right? And then coming up with the answer. Okay. An even tougher task is, it's not enough if the system comes up with an answer, we want the system also tell how that answer has been generated, why that particular answer has been generated, right? This is what is called as the reasoning task, and typically we use the common sense to come up with the reasons. So in this example, I give this image, then first I ask this question, where is this happening, right? To make the task simple, right? Let's say I give 4 options, and I want one of these 4 options to be chosen as the answer, right? Obviously, the answer is option C here, right? And once I say that this is the option, correct option, right? Then we want the system to tell why you have come up with this answer, right? Again, to make the thing simple, we give options for the reasons, right? We call them as the rationale. And among these 4 options for the rationale, the system should tell which of these 4 options is the correct rationale. Okay? And this is even more tougher task, right? Mainly because it involves understanding the content of the image, understanding the question, then generating the answer, then coming up with the explanation of why this particular answer is picked for this question and for the image. Okay? And interestingly, one can explore many of the deep learning models to perform this task, right? And it's a combination of the CNN models and the sequential data processing models, as we'll see later, right? There are other types of sequence processing models like what are known as the transformer models. One can put all these models together, right, to build either the visual question answering system or a visual common sense reasoning system. Okay. Any questions at this point? Yeah. Sorry?
Chain of thought.
Chain of thought. it's even more complex task. Right? So basically, I'm not sure whether the example that I'm going to give you will involve exactly the chain of thought, right? Let's say you're talking about something like a text summarization task. I give maybe 1 page long document, right? Now I want to generate a summary of that document in maybe 3 or 4 sentences, right? So that involves not only understanding the content of the text, right? You also need to understand what is the flow of the thought in the generation of the content of that text. And then you should pick up, in the extractive summarization, we pick up only subset of sentences from the original document, right, in order to prepare this summary. But there are other types of ones where you generate the complete summary independently, but that will summarize the whole text, right? So that involves, right, capturing the line of thought, right, and then use that to generate the summary. In the same way, when you talk about video summarization, right, I mean, you can consider this video summarization also as some kind of a video captioning task, right? There, it's not just identifying the events and then coming up with the captions, right? You also need to link them up and then generate the summary. Okay, so generally for the summarization task, we need to capture the line of thought.
All these models have the data set with these options for the reasoning also.
In the standard VQA or the visual common sense reasoning, where there are 2 types of systems. One is only the multiple choice types, right? Then the other one is what is called the open-ended systems. Okay, in the open-ended systems, we are not giving the multiple options. We want the system to generate either the answer or the reason, right? And that is a much more complex task, right? So that's where it requires some kind of a line of thought to be captured, right? And then used to generate the answers.
The data set this is model, right? That is
Unfortunately, we have only the training examples, right? So for a number of examples, I can collect the image, I can collect the question, I can collect the answer, right? No, I can also collect the rationale, which are given by the humans.
rational is given in the form of multiple choice as
No, not necessarily. It can be open-ended.
open.
Yeah. Now one can train the system with all these inputs, right? And then after training the model or training the whole system, then when any new image is given and a question is given, right? Then the system will generate not only the answer, it will also come up with the rationale for that, right? So
Just asking on the
uh,
below 30%.
you're on the optimistic side. Yeah, actually, the racial identification is not really performing that well, right? It's a very, very complex task, right? Yeah, yeah. The systems are not very highly successful yet, especially in the open-ended case, right? If it's a multiple choice type thing, right, it's been fairly successful. Yeah. Okay, good, very good. This is nice person. Okay. As we saying, the sequence-to-sequence mapping tasks play a very important role in performing many of these tasks, and many of the tasks in the text processing actually map onto this sequence-to-sequence mapping task. Okay, what do you mean by sequence-to-sequence mapping task? The input is a sequence and the output is also a sequence. So some of the text processing tasks actually happen to be the sequence-to-sequence mapping task. Not all the tasks. Like if you take the machine translation, where you're talking about translating text in one language to a text in another language, you have a input sentence of a source language, and the translation system is expected to give the sentence in the target language. And the lengths of sentences need not be the same in the 2 languages, right? So basically, you're mapping a sequence of the input source language sentence onto another sequence, which is of the target language sentence. So now, if I collect a number of pairs of sentences like this, what I want the system to do is do this mapping from source language sentences to the target language sentences. And this occurs naturally in the machine translation. And interestingly, we can pose the video captioning also as a sequence-to-sequence mapping task, because video is a sequence of frames and the output caption is a sequence of words, right? So I can pose it as a sequence-to-sequence mapping task. And then we try to use this sequence-to-sequence mapping models to perform these tasks. So one way of solving this sequence-to-sequence mapping tasks which have been explored for the years is what is called the encoder-decoder paradigm again. But you can see that now both this encoder and decoder are based on the recurrent neural networks because both input and output is a sequence now. Okay, so you have the encoder which is in the form of an RNN which takes the input sequence and then generates a representation of that, and that representation goes as the input to the decoder RNN that will generate the output sequence. So let's say if I'm translating sentence from Hindi to English, right? So all the Hindi sentences will go as input to the first encoder module. Then this decoder module is trained to generate the English sentences. And typically this sequence mapping basically tries to capture the relationship among the elements of the sequence. Right, we'll be trying to look into what do you mean by these relationships. And typically, there are a number of elements in the sequence. What do you mean by this? Suppose you have a sentence. Sentence is a sequence of words. So we consider the words as the elements in the sequence. If it's a video, right, the frames are the elements of the video, right? And what do you mean by capturing the relationship between the elements of the sequence? When you have a number of words in a given sentence, I want to see what is the kind of relation that we have between different pairs of words in the sentence, right? So there may be nouns, there may be verbs, there may be adjectives, and so on. So now I want to see how to capture the relations between these words. And similarly, in the case of the video, I want to see what kind of relation is there among the different frames in the given video. So basically, the sequence mapping tasks try to focus on capturing the relationship among the elements of the sequence, and then try to use that to perform the mapping task. And there have been many successful systems based on the LSTM models, and but they are computationally very intensive, and also they require huge amounts of training data. And also, there's not really much of scope for parallelizing the operations so that the training can be made faster. And in 2017, one paper with a very small title, which has generated a lot of interest, and it's kind of changed the landscape of these deep learning models. That's what's called the transformer models. And the title of this paper, which introduced these transformer models, is "Attention is all you need," right? And that has kind of triggered a new line of research in the deep learning area. And there are so many systems based on the transformer model that has been proposed in this paper nowadays that are being explored extensively for many of the deep learning tasks. And we'll be looking at how to do this sequence-to-sequence mapping tasks using this what are known as the attention-based models. And as I said, we are trying to capture the relations among the elements of a sequence, and we use these attention-based methods to capture these relations. And if you are capturing relations among the elements in one sequence, then we refer to it as the self-attention. So we are doing this sequence mapping task. You have the input sentence, so you want to capture relations among the elements of the input sentence. That's the self-attention. And similarly, there is an output sequence, and you want to capture relations among the elements in the output sequence. So that's also a self-attention. But in order to do this mapping task, you need to relate the input sequence to the output sequence. Basically, you need to relate the elements in the input sequence to the elements in the output sequence. And that we try to do by performing another type of attention called the cross attention. So basically, as we'll be saying, we do the self-attention on the input, and we do the self-attention on the desired output. And then we also do the attention to capture the relation between the input sentence and the desired output sentence, and then use that to perform the mapping task. This is a familiar diagram you'll come across whenever you see this paper, right? And I wanted to spend a minute to look at what are the different blocks that are present in this, right? Yeah. Any familiar names there? Yeah.
Normalization.
Normalization. Okay, good. Straightforward. Okay, good. Softmax. Okay.
Linear is there.
Linear is there. So what is not familiar here?
Multi-head.
Multi-head attention, right? So you can see that what is called the multi-head attention here, right? Again, what's called the multi-head attention here, and also the multi-head attention here, right? And then what's called the masked multi-head attention here, right? So what is first multi-head attention does is, as you can see here, this is part of the encoder module, right? Basically, this multi-head attention captures the relation among the elements of the input sequence, right? And this masked multi-head attention is used to capture the relation among the elements in the desired output sequence. And once you get this representations of the input sentence and the desired output sentence, as you can see there is another multi-head attention here, which performs the cross attention, where it combines the representations of the input sequence and the desired output sequence, and then uses this relationship to perform the task here, that is to perform the translation task with the machine translation that you want to perform. Okay, as you can see here, the input is a sentence or a sequence, and output is also desired output is also a sequence, and the final output is also a sequence. Of course, it generates only one word at a time, right? And then it continues until the end of the sequence generation. Okay. You said that all other terms are familiar here. Yeah.
There's one shifted right. What is it?
Yeah, we'll come to that. Okay. Yeah. Because it's generating only one word at a time, right? You generate the first word, right? Then you use that first word in order to generate the second word, right? So when you have the desired output during training process, you have the complete desired sentence, right? But you are not going to use the complete sentence in training the model in a single step. So you take the first word, use that to generate the second word, then you shift by right by one position and then process that. Okay, that's why it's also called the masked attention. Okay, yeah. Right. As you'll see later, this attention is basically a linear operation, but the linear models are not going to be good enough to solve very complex tasks. You need nonlinearity also, right? So where do you think the nonlinearity is coming from? Activation functions. Yeah, where do these activation functions come into picture here? Yeah. No, multi-head attention, as I said, it's going to be a linear operation. Feed forward, right? So the reason why this feed forward is present there is mainly to introduce the nonlinearity. Okay. Yeah. I just wanted to have this high-level picture. Now we'll go into the details of this transformer models. I understand that there is going to be very detailed sessions on this transformer models. I'll give you some kind of a summary of the principles of this transformer. So this attention models are basically using what are known as the scaled dot product attention, and the terminology for the scaled dot product attention are actually borrowed from the linear regression methods that have been used for the function approximation. Let's say I have some examples, xn and the desired output of yn. Then for any function approximation, that's what the any examples, right? Now I have a new example x for which I want to predict what is the value of y. What we do here is we relate this query x to one of the training examples, then see how similar they are, then use this similarity value to weigh the corresponding desired output of this training example, right? So basically this g of x comma xn is a measure of similarity, and I use that as a way to multiply the desired value for this example xn. Now we can see that the summation is over all the training examples that we have. So basically what are we doing here? I have the query, I am matching that query with one of the training examples, looking at how similar they are, then use that as the weight, and I use that weight to multiply the desired output of that training example and use that to perform the prediction here for new x to generate the y. Okay. So we have the terms like query, key, and value. As you'll be seeing, we'll be making use of these terms in the attention-based models. And so what do we have in this attention-based models? We typically have a sequence of vectors, right? How do you get the sequence of vectors? Let's say if I have a video, I have a sequence of frames. What is each frame? It's an image, right? Now, can I get a representation of an image? I can take the output of a CNN model, or I can use any other method to extract the features and then generate a one feature vector to represent that frame. And the number of frames can vary from one video to another video. So that's why we have a sequence of some d-dimensional vectors where they are associated with the time index small t, which varies from 1 to capital T. Now, if it is a text, if it is a sentence, what does this representation correspond to? Yeah, words. Then how do we represent the words? Again, we need to have a representation of words, right? There are a number of methods of encoding the words, like word to vec is one of the most commonly used one. There's also what is called a globe representation and so on. Doesn't matter, right? Use any of these methods to generate a representation of the words. So if I'm given a sentence, now I know how to represent that sentence as a sequence of feature vectors. Okay. Now what I want to do is take the sequence of feature vectors and then do the processing, right? So I'm going to take the input feature vector at some time t and then generate these three new entities, right? From that representation of the entity at small time t, I will call it as the query vector, key vector, and the value vector. We'll be seeing later how these vectors are going to be generated. We'll come back to that later. All right. Now, what I want to see is how to relate the query vector with the key vector and see what kind of a similarity is there. And then, similar to what we have done in the functional approximation task, we'll use that similarity measure as a way on the value vector. Okay. As all of you know, one of the ways of measuring the similarity between two vectors is by computing the dot product. All right. So that's why we compute the dot product between one query vector qt and one of the key vectors km, m key vector. As you can see here, the numerator term here is the dot product between qt and km, right? And I don't want it to be, as all of you know, what is the dot product here? We take the product of every pair of elements, right? Multiply them and then add them. As the dimensionality of the vector changes, the value of this dot product can change, but I want the similarity measure to be kind of independent of that dimension. That's why we define and we divide that by the entity related to the dimension here. That's why it's called the scaled dot product. So basically, this scaled dot product gives us some kind of a measure of similarity between these two vectors. One is the query vector and the other one is the key vector. Now I generate what is known as the attention score using this softmax function. Why do we do that? Yeah, you can interpret it as probabilities, but here we don't have probability, right? Yeah, it gives what's called a normalized score, right? Because what are the values of this softmax function outputs? They are in the range 0 to 1. And when you look at this scores for all the m indices here, right? Then they will add up to 1, right? So basically what you're doing is, we take this alpha tm with respect to every m, right? And once we get that, right, then we use this softmax expression to get what is called the attention score, which I'm calling it as the ATM. Again, please note that it is still between one query vector qt and the key vector k. But one thing is, instead of scale dot product, I'm going to use the softmax function to get the entities in the range 0 to 1, and which will add up to 1. That's what's called the attention score. Now, I'm going to use these attention scores and the value vectors to generate a new representation for the entity at time t. So basically, we generate this what is called the context vector associated with this query vector qt as ct. As you can see here, what is the expression for ct here? It's alpha tm, atm multiplied by vm. Vm is the value vector associated with the mth key vector, like what I said in the functional approximation case is the kind of desired output. So this ATM acts as some kind of a weight. So I'm looking at the weighted entity of this value vectors and then add all of this over all the vectors of the key vectors, and then generate this CT. So basically what the CT is trying to do is, it is looking at how this query vector is related to each of the key vectors, right? And then it's generating a new representation for that QT. But this new representation is based on only the similarity, and that similarity is obtained by this scale dot product attention, right? And what we get here is what is known as the context vector. So basically for every query vector QT, I get this context vector CT, which is obtained by performing this scale dot product on QT. And because we are using all the key vectors and the value vectors, all of them put together in this matrices K and V, that's why the CT is a function of this capital K and capital V. Okay. So basically for every QT, I'm generating now a new representation called the CT. Okay. Good. So now we talk about what is known as the self-attention and the single head attention. Why do you call it self-attention? Because I'm going to take the elements of the same sequence and then perform these operations. That's why it's called the self-attention. Now we introduce this term called the single head attention to see how these query vectors, key vectors, and the value vectors are generated. As you can see here, I take a particular entity at time small t, xt, then I'm multiplying that by a matrix. Right? So what is the result of multiplying a vector by a matrix? It's also another vector, and the elements of this matrix are some numbers, right? So what is the nature of relation between the QT and XT now? Is it linear or non-linear? You are multiplying XT by some matrix W, where the elements of this matrix are only some numbers, right? So basically, we are performing some linear transformation on XT to get QT, right? Now, I use the same XT to generate all this query vector, key vector, and the value vector. But what is different here? I have different matrices here, WQ, WK, and WV, right? So basically, I'm generating this query, key, and value vectors, all of them from the same XT, but by using this different transformation matrices, right? And once we get this query vectors, key vectors, and value vectors, I use this to perform this scale dot product attention and then generate this context vector, right? Now, these matrices WQ, WK, and WV all put together forms what is called a single head, right? And I'm going to use one linear transformation here, one set of linear transformations here to generate all this query, key, and the value vectors, right? And when I do that, I'm performing what is called the single head attention. So the single head attention generates one context vector from every query vector, right? And that uses all the key matrices and the value matrices. That's what is pictorial represented here. As you can see here, the XT is passed through this WQ, WK, and WV. We generate all these three vectors. Then I perform the scale dot product attention and then generate this context vector, right? In the neural network models, when we have the hidden layers, what is the purpose of the nodes in the hidden layer? To extract the features from the input. Why do we use multiple nodes in the hidden layers? Because we want to extract multiple features, right? The same way here, when I do this transformation here, I'm doing only one type of transformation, so it extracts one kind of representation, right? Why should we limit it to only one, right? So now we come to what is known as the multi-head attention, where I do this kind of operations, right, using multiple sets of these transformations. Now you can see that there is what is called WQI, WKI, and WVI, where all these entities are associated with one head. The moment you change these transformation matrices, these entities are going to be different, right? So for the same XT, right? Now for the different heads, you're going to have these different vectors, right? So the context vector that generated is going to be different. Now it's called as the CIT, which means that is the context vector that generated using the ith head. Okay. So now you can see that I'm going to use some number of heads, which means that I'm going to use some number of sets of these transformations, and all these transformations are going to be different, right? So that will enable us to get some new representations, multiple representations for the same vector XT. And typically, this number of heads is related to the original dimension D, right? And as we see later, the dimensionality of these vectors of the query key and value vectors is typically in L, where L is E by H, right? And what does that mean? What is the size of this matrix in W? What is the XT dimension? D, right? But you want to generate these query vectors on the other vectors of dimension L, which means that these weight matrices are going to be L cross D, okay? And each of these transformations will lead to some L dimensional representation of this XT. And what we are going to do is we are going to put all of them together, right, to form the new representation of a particular example, right, as we'll be seeing later, right? We are doing the concatenation here. How many context vectors we are getting? H context vectors we are getting. The dimension of each of these context vectors is L, right? When I concatenate all of them, I'll get back again a D-dimensional representation, which is the same dimension as the original dimension, okay? Yeah, so basically we perform this multiple header attention to generate a new representation of every XT here in the form of this context vector, right? And then we do one more linear transformation to generate what is called the Z as the representation. And in all of this, what we are doing is nothing but performing some linear transformation, then using the attention to capture the relations, right? So that we are looking at how similar is each of the elements in the sequence to the other elements in the sequence, and then use that relation to capture the new representation. Okay, again, pictorially, this is what we are doing here. As you can see here, there are multiple heads here. I take the same XT, right, and pass it through these multiple heads, and each of them generates a context vector. I put all of them together to generate the overall context vector, and then perform one more linear transformation, which will generate the final representation of this XT in the form of this Z. Okay. As I said, all these transformations are only linear in nature, right? And linearity is not good enough, right? So we try to introduce the non-linearity now. So basically what we have done, earlier we have generated this Z vector by multi-head attention. Now I pass it through a feed-forward neural network, which all of you are familiar with, which typically has an input layer, then a non-linear layer, and an output layer, right? And then it will generate a new representation for the original XT in the form of this X tilde T, right? And this we can do in parallel for each of the elements, right? This is where there is a lot of scope for parallelism, right? And can I do all these operations also in parallel here, right? So that's why these models provide a lot of scope for parallelizing the operations, and many of these things are kind of run on the GPU machines, right? Where you can use the GPUs for parallel performing certain several parallel operations. Okay. Actually, all of this, what we are doing here, forms one layer of the encoder or the decoder, right? So what is we have done? We've taken a sequence, right? Then performed all this self-attention, multi-head attention, and then use this feed-forward neural network, right? Then generate a new sequence from this, right? And all of this involves one set of linear operations followed by non-linear operations. Again, one non-linear operation is not adequate. That's why you typically have multiple layers in a neural network, right? So we do the same thing here. We build an encoder module where there are several layers, where each of these layers have the similar structure. So we take the input sequence. The first layer will generate a new representation, X1 tilde. That new representation goes as input to the second layer, and then it will generate yet another new form of the representation, X2 tilde, and so on. If there are some L number of layers, then at the output of this Lth layer, we get the final representation of this sequence, right? So basically, transform this sequence X to this sequence XL hat, where we are generating this new sequence which captures the relations among the elements of the sequence, and then performs this multiple head attention followed by nonlinear operations to generate a completely new representation for the input sequence. Okay, and all of this is being done by using only sequence of transformations, right? Linear as well as non-linear. That's why we call this as a transformer model. Yeah, any questions?
Can we apply this in any sequence data?
Yes, any sequence data. As long as you have a meaningful way of representing your data in the form of a sequence, right? And you know how to represent each element of the sequence by a vector, right? You can use this model, right? They've been initially explored for mainly the text processing tasks, but as I will be showing you later, right? I can use it now for the image tasks as well as for the video tasks, right? And any type of sequential data that you have, right? You can use this. No, so typically when you say sequence, it's in order, right? So in the case of the text and video, you have the temporal order, right? But in other types of data, you may not have temporal order, but you have some other order.
If it's a time series data, we can.
Yeah, obviously, time series of data will have temporal order, right? So any type of sequential data is fine.
We have used it for text.
Okay, yeah, good, yeah. Sorry? Yeah. No, he was only making a comment that they have used this model. Oh, unlike that's the question. Okay. Yeah.
Please read.
Sir, can you please explain how queries, keys, and values are combined for a time series data?
So basically, for any sequential data, what we get is this x1, x2, so on, x capital T, right? And from this elements of this sequence X, we perform this multiplication by these matrices associated with the heads to generate the query key and vector, value vectors. And all these W parameters are all learnable parameters. Okay. Like in the case of neural network model, we have the weight parameters. Here also we have the weight parameters. And that's why these are named as the W's, right? So they are initialized to some random values initially, right? Then you go through the training process. And at the end of the training process, you have the elements of these W's are also being learned. Yeah. Does that answer the question? Okay, good. Yeah. Any other questions? Okay. Good. So we do similar operations in the decoder, right? So in the case of training phase, we have a desired sentence, a desired sequence. So I take the desired sequence and then perform this same self-attention, multi-head attention. The reason why we call it as masked attention is that typically we generate only one word of the output at a time, right? So we kind of simulate that scenario here. So I take only the first element here, right? And then, of course, for one element, there is no sequence. Let's say when I come to the time instant 2, I have both y1 and y2. So I'm masking all the later elements, right? And then performing this attention-based operations only on the partial sequence of the time t. And then I'm generating the new representation of that partial sequence that will combine with the representation of the input sequence and then perform the cross attention. And then again, I have this nonlinear transformation, and the output of this nonlinear transformation will be used to generate the next output at the time t. Okay, and we do this until we reach the end of the sentence, right? And we should calculate it. Yeah, our sequence of time t is what's shown here, right? So basically, we do the similar operations like what you have done in the encoder module, except that we do this masked self-attention, and then we do the cross-attention between the input sequence and the desired output sequence, and then we perform the nonlinear operations to generate the new representation of this partial sequence here at time t. And again, this is only one layer in the decoder. We have multiple layers typically, similar to the encoder layer. And at the end of this L layers, we have the new representation that captures the relation between the input and the desired sentence. And then we pass it through a linear layer and sequence layer to predict the next element in the sequence. So basically in the training phase, the desired sequence is given as the input to the decoder module, but in the testing phase, output sequence is generated only after time t, and that's given as the input to the decoder, and then we predict the next element in the output sequence. Okay. So this is basically now you know what all these elements are. Okay. Okay, so one can use this transform model for any sequence to sequence mapping task, like machine translation is one of the uh, tasks for which it has been explored very heavily, and there are a number of attempts to perform the video capturing task using this transformer models. Will have a look at it. Okay, now I'm going to tell you how I can also use this transformer models for several other problems of interest in the image and the visual processing domain. There is an interesting transformer model called the vision transformer. Actually, it's a kind of an overloaded term. Okay, so this is basically designed for the image classification task. But as you see, the transformer models require basically a sequence as input. But once, if I have an image classification task, I have only one image as the input. Now I have to kind of generate a sequence from this image. So what is typically done is I divide the image into patches and then put all these patches in a particular order to form a sequence, right? So let's say I have a 100 by 100 pixel image, right? Then I divide that into, let's say, 20 by 20 pixel patches, right? So then I have 5 rows and 5 columns, right? So that will give me 25 patches. Then I put them, these patches, in a particular order and then generate a sequence of 25 patches. And I generate one feature vector for each of these patches to generate a sequence of feature vectors, right? And that I use it as input to the transform model, and then it generates a representation of this, and that representation will go as input to a multi-layer perceptron network, right? Which can be used to perform the classification task. So basically, we do this transformer encoder-based multi-head attention, and this representation of the image as a sequence of patches, and then perform the classification task, right? It is also what is known as a swing transformer, which is called the basically swing stands for the shifted window. Basically, it processes the image at the different resolutions and then performs the feature extraction using these multiple resolutions. And some studies have shown that this swing transformer performs better than the vision transformer for many of the classification tasks. Yeah. My interest here is how I can perform the image captioning using these models. Okay, so now we perform this image captioning using transformer, right? As we've seen earlier, typical image captioning involves 2 phases. One is the encoding and the decoding. Now I use the vision transformer to perform the encoding. That gives me a sequence of vectors that represent the content of the image. Then I take the transformer decoder, which has been trained to generate the text, right? So now I put the vision transformer based encoder of an image and the transformer decoder for the text, right? To perform this task called the image captioning. And everything is now mapping from an image represented as a sequence of patches onto another sequence which corresponds to the sentence for the caption of the image. And one can generate a very detailed caption for an image that is referred to as the image paragraph captioning. Like in this case, if I am given this image, if I ask a human to generate a caption, maybe this is the kind of caption that's generated, like saying that there are 2 elephants standing on the ground, there are 2 people standing next to them, one of the elephants on the left has its leg raised up, there are green trees behind the fence, and so on. Okay, and interestingly, a system that has been built to perform this paragraph captioning has generated a much more detailed caption than what a ground truth caption is. It all depends on what the system has been trained with. Okay, as you can see here, there are 2 modules again here. One is the vision transformer encoder that represents the image, and then we have the transformer decoder, which has been trained to perform the paragraph caption generation. Again, there are a number of papers of this, right? Those who are interested. And one of my PhD students has worked on performance video captioning using multimodal attention, and where we take the different modes of representation of the video, like we identify the keyframes in a given video, we identify the objects, and we also get some kind of a semantics representation of the content of the video, and then combine all these different model inputs using the transformer based techniques right? And then build a model to perform the generation of the caption for a video, and the details of that are available. I mean, it has been accepted now. Okay. And for video captioning, especially if you want to generate a very detailed caption, then one can go for the dense video captioning, right? Again, there's a paper which talks about dense video captioning using the CNN models and the transformer, right? So basically, I use the CNN here to get the representation of every image, right? And that sequence of representations of the frames will go as input to the transformer model, and then it is trained to perform the captioning task. Again, there's a paper on that, end-to-end dense video captioning using the master transformer, right? And there is also some work done on how to reduce the number of parameters in the transformer model, right? So there is a model called the DELIGHT model, which stands for the deep and lightweight transformer, which instead of using multiple heads, it tries to build a whole system using a single head, but maybe a larger transformation side. Okay. Again, those who are interested can refer to this paper. And there's a paper on machine translation using this DELIGHT. Okay, good. Now we'll come to one more important aspect of this deep learning models. Though we have solved the problem of training the models faster by going for the parallelization operations, right? Both in terms of the multiple head operations as well as the parallel operations by the position-wise operations. There is still a requirement of large amount of label data when you want to train these models, right? And getting a large amount of label data is not easy. When I say label data, let's say if you want to do the translation task, you need to have a large number of pairs of sentences. Or if you want to use the video captioning system using these transformer models, then you need to have a large number of videos and the corresponding captions generated by humans to perform the translation of, to perform this task. Okay. I mean, as with the many other deep learning models, there have been a lot of attempts on how to deal with this requirement of large amounts of label data, which is very difficult to get. So most of the deep learning models have explored what is called a two-phase training. First one is what is called a pre-training phase, which can be done in an unsupervised manner, which means that I don't have to have the labeled data. I can have only unlabeled data and then perform the pre-training. And once we do the pre-training, then if we have small amount of labeled data, then you do what is called a fine-tuning. Okay. Actually, there are what are called the stacked autoencoders, which have been developed for the pre-training of the standard deep fit for neural networks. But in the case of transformer models, we need something where it suits the purpose of building these models for the sequential data, right? So there's a lot of focus on how to do this pre-training for the transformer models. And one of the extensively used models is known as what is called the BERT model, which stands for the bidirectional encoder representation from transformer. Basically, this is an encoder that's used for pre-training with only the text data. All right, as we'll be seeing a little later, right? I use some unlabeled data. When I say unlabeled data, like I have some sentences in a language, right? There are no corresponding desired output sentences, right? I just use all these sentences in a particular language to train this model so that the information about these sentences is captured by the model. And this is mainly for the text data, but when we want to use these transformer models for the image and video task, we need something similar for the visual data and also the linguistic data, right? So there is also a version of this BERT model called the Wilbert model, which stands for the vision and language, right? And this bidirectional model is basically, it is looking at the relation of the pairs of words irrespective of where the words are present, right? That's why it's called the bidirectional model. And there's a, of course, very popular one, right, called the GPT, which all of you know that the GPT is very popular. And it's also a model that's mainly built for the pre-training, right? It's called the generative pre-trained transformer, but it does some kind of a unidirectional operations. Basically, it tries to predict the word at a particular time t using all the prior words, right? And that model is what's called the generated pre-trained transformer, but that's mainly used in the decoder phase of this transformer. So basically what is done in this BET model is, as we said, it takes some sentences and there will not be any corresponding desired output sentences, but I use only this set of sentences to train this model. So one of the pre-training methods is what is called the masked language modeling. As I take a sentence, then I mask a few words in the input sentence, right? Then I want the model to predict all the words that have been masked. Okay. Now you can see that I need only a sentence. I don't need any corresponding desired output sentence here, right? So basically this system has been, or this model has been trained, right? How to predict the masked elements in the given sequence. Okay. That's one way of doing this pre-training. Another one is next sentence prediction. Suppose I have the text. There'll be a number of sentences, right? And every sentence is followed by another sentence. Now we take every pair of sentences here in the text, right? Let's say it's a sentence A and sentence B, right? Now I give a sentence A and I want the model to predict the next sentence, right? Please note that there's no what is called the desired output sentence here. All these sentences are, let's say, it's a machine translation task, right? I'm talking about sentences in one language, right? So basically, we train this BET model, which is nothing but a transformer model, but it's only the encoder, right? But we train this model using only unlabeled data. And once we do this pre-training, right, then depending on what task I want to use this system for, now I can use it for any other tasks like sentence classification, or sentence relationship capturing, or textual question answering or translation, so on, right? So this BET actually the pre-training method, right, for mainly the text processing tasks that involve the natural language processing tasks. So once we do this pre-training, then for whatever task that I want to use this model for, then I do the fine-tuning depending on what the task that I am interested in. So in the case of this Wilbert, I have two modes of input. One is the visual input, that's a sequence of frames. The other one is the corresponding sentence, right? Now I have a pre-trained model which takes both these as the input and then estimate the parameters of the model, right? And then once I use this, or once I train this model, then for any new video data and the corresponding sentence, right, I pass it through that, and then there's the representation of that, right? Again, there's the encoder module and the what's called the co-attention transformer layer, which forms as the Wilbert to perform this task. Okay, I think I'm going to skip this. Okay. We'll take a few minutes to look at the other challenging tasks that we wanted to solve using these models. As we said earlier, we are interested in solving this visual question task as well as the concepts task. Now let's see how I can perform this visual question task using what are the models that we have looked at. So basically, I need an encoder for the image, right? And I need an encoder for the text. So I can use any of the combinations of the models that I have. Like for the image encoder, I can use a CNN or a vision transformer or a sprint transformer. For the encoding the person, which is the text, I can use in a recurrent neural model, or I can use the encoder transformer, or a BET model that's fine-tuned, right? And so on. And once I get these two representations of the image and the person, then I combine these representations. Again, there are a number of methods available for the fusion. And after the fusion of these representations, then I have a module called the concept generator module, right? If it's a multiple choice type questions, right, then it will be a simple classification model, right? Of course, if it's a open-ended VQA, right, then this has a generator model. Okay. So typically, we do the answer generator using classification model with a multiple choice type question. Otherwise, text generator such as the GPT, right, to perform the answer generation. So there are a number of papers available, right? So the case of this paper where we are talking about this visual question answering, again, I use a CNN model to process the image and a LSTM model, and then combine these representations, and then I have a classification model to generate a multiple choice. Okay, and one can also use a Wilbert model to pre-train model, right? And I can do the fine-tuning for this task, and then once I have the representations of the combined image and the person, then I will train this answer generated model to perform this task. So when we say open-ended VQA, as we said, we have an image and then we can ask a question. In the case of the multiple choice type question answering, I am giving the options and then I'm asking the system to select only one of the answers. But the open-ended VQA, I want the system to generate an answer, which is a sentence. In this case, I want the answer to be something like the zebra is grazing the grasslands, right? Whereas in this case, the question is what is in the dog's mouth? The answer can be something like the dog is playing with a toy in his mouth, right? So basically, this requires a text generation module which generates one word of a text at a time, right? So one can use a GPT model kind of thing, right, to perform this generation. And one can extend this for the video data as well. And we can also have the video question answer system. And interestingly, there are attempts to make use of the captions of the images in the question answer system. So basically, I have an image, I encode that. I have a question, I encode that. Then I also generate the caption for this image, then generate the caption. Then because caption has captured the content of the image in terms of text, right? I make use of that. So basically now we capture the relation between the image and the question and the caption, and the image and the caption. And then make use of all these relations to perform this question answering task, right? Again, this has been shown to be more effective than the systems that don't do the caption. So finally, we have this complex task, visual common sense reasoning task. And there is a framework available there where I have the multiple subtasks here where I need to relate the question to the answer and question and answer to the particular rational, so that finally, when I am given a question, I can relate it to both an answer and as well as the rational. Okay, and typically one makes use of a number of these deep learning models put together, right? I'm showing you one example here where the C schemes are used and the BET models are used, right? Where this is one of the most extensively defined the paper for this common sense reasoning, which is titled as the From Recognition to Cognition. Recognition is a simple task like classification, but cognition is understanding the content of both the image and the text, right? So there are basically three phases here where we take the image, get the representation of that, then we get the combined representation of the question and the answer, and the outputs of these encoders is processed in the three different phases. One is called the grounding, then contextualization of question, response, and the image regions, and then it's used to train a model that generates the reason, right? So in this question, in this case, this is the image. The question is, why is person 4 pointing at person 1, right? Now the answer is because he is telling person 3 that person 1 has ordered some item. Okay, and basically this different terms here, like when you say grounding, query, and answer, they are trying to capture the relation between the image and the question and the corresponding elements of the answer. And basically we have the query and the answer, which are nothing but the question and the answer. They're trying to relate the words in the question and the answer with the objects in the different objects in the image. That's what is called the grounding. Then we use the certain mechanisms to contextualize the query and the answer with respect to each other. And basically we are trying to capture the relation between the question and the answer. And in the reasoning, we are trying to capture the contextual representation of the objects, the image, query, and the answer, as well as the rational, right? So that it can come up with the answer for the rational. Okay, that's all I have.
Previous slides has some questions.
Yeah,
Lot of
please.
things are there. Actually.
Of course. Yeah. I taken only 10 seconds to. Yes. Okay. Yeah, of course. One can go through the paper for the all the.
That grounding actually made me to recall a very popular model in question answer called bidirectional attention.
Mhm.
Then I don't really get how it is different from the contextualization.
No, as stated here, what we do in the grounding is we are only grounding the query and the answer, right? Basically, what are we doing here? We are taking each word in the query and answer and just relating that to the different objects in the image.
Yeah. finding which word in the answer or the query
Is related to the which object in the question, right?
Then,
What we are doing in the contextualization is we are also capturing relation between the query and the answer.
between
Yeah, here we are not capturing relation between query and answer, right? We are only capturing relation between query and the objects of interest in the image.
it's like attention between two textual components.
No. Here in the grounding, it's only
No, contextualization.
in the contextualization. Yeah, in the contextualization, yes, we are
And the image.
and the image also. Yes.
So is it like the same thing done again, or the way in which it is done is different?
No, as I said here, for each word in query, we compute attention score with respect to each word in answer.
Yes.
Then perform attention with query and the objects in the image, and also between answer and the objects in the image.
So, the number of parameters would blow up, right?
No, number
So
of
many things are being done.
obviously,
Obviously,
it's complex task. So it requires a complex system.
after this much of complexity in the number of parameters, I'm still doubtful. I have not read this. In terms of the way it is really understood. Again,
Yeah. Okay.
statistical
No,
pattern.
as shown here, of course, this is a particular implementation where we have a CNN model, where you have the BET model, and where you have a couple of LSTMs. Okay, but in principle, all these LSTMs can also be replaced with the transformer models. Okay, now obviously the number of parameters is going to be huge. Okay, but we can still handle that in terms of the number of training examples required by first going through the pre-training process, right? And then only doing the fine tuning using the labeled data.
Let's see. That's your rich.
Yeah, you need to be.
Lot of GPU.
No, you need to be rich in resources. Yes. Okay. Yeah, that's why most of this work involves making use of GPUs, right? And you go for all these collabs and so on, right? That's why it's very difficult to beat the companies like Microsoft or Google, where they have huge resources, right, to develop these systems, right? Whereas all the academic institutes are poor institutes, okay, in terms of the resources. But I think we make use of the other resources. Yeah.
But anyway, the BERT is a pre-trained model, right?
That is a pre-trained.
It is a pre-trained model.
Yeah.
So I think.
No, but still.
Even then.
Yeah, no, it's a complex system. I'm not undermining the complex system here, right? As I said, it's a complex task, so you need a complex system, right? See, about 10 years ago, we never even thought of this kind of tasks, right? We are mainly focusing on classification tasks, annotation tasks, and so on, right? Only with the advent of these deep learning models, we started looking at more complex tasks. Of course, because the complex models are available, the resources are available, right? And we are trying to solve challenging problems here. That's what I'm trying to say, right? As we asked sometime earlier, right? I have not presented the details of what is the performance of these models, right? So for the open-ended VQA, the performance is not really that great, right? Whereas for the restricted question answering, that's multiple choice type question answering, and also the rational, performance is reasonably good.
Yeah, I think I support her in many aspects of it, because the hardware is going to cost more than 5 times. Even the cloud to get it with the GPU.
No, but please understand that
even with the
all these hardware and resources are required only for training the model. Once the model is trained, right, the inference phase is not going to be taking much of time.
Certain models to run on, for example, even a pre-trained model to download and run on a machine, right? Even that is going to doesn't support certain GPUs.
In all the tasks, we want to present the positive things.
Right. Dolo model, right?
Huh?
Dolo model is actually taking more than 8 to 12 GP of GPUs.
Our students come and cry.
I've seen practical difficulties.
Yes, yes, of course.
You had to go for Polar, and that to a paid version of.
Yeah. But for every problem, we come up with a solution. Yeah.
What about the flexibility of these pre-trained models? Like earlier, we had to build something from scratch. We could control all the hyperparameters. Like for every layer, we could control some things that we had. These pre-trained models come in.
See, once you want to use the pre-trained model, there's not much of flexibility, right? Because that model has been pre-trained for some architecture.
But is there a scope to like tweak the internal hyperparameters so that we can fine tune it?
No. See, let's say if you have a bet model where you have used 4 heads, right? Obviously, you can't build another model with 8 heads using a pre-trained bet model with only 4 heads. There's no way you can change the configuration because that model has been pre-trained only for the configuration of with 4 heads, right? So the fine-tuning is only for making the model suitable for the data that you want to use in your domain, right? Yeah. So if you want to build a new configuration, then you have to go through the complete training from the scratch. Yes. Yeah. No, but if you have the resources, then you can go back and go through this complete processing from scratch. Well,
What is multi-model? Like, what we are saying is GPT-4 and Google released a new multi-model.
multi-modal, I think they're referring about the different modes of inputs. Like I was talking about the video captioning multi-modal, right? So for same video data, I have 3 different types of data coming in, right? Like keyframe and
Will there be only one model?
No.
Should we also use
No,
VNM?
I think what you're referring to is the multi-modal, MODA, not MODE. It's a single model, but multiple modes of it.
How it is?
I don't understand.
That means the data will be coming in 4 formats like
No, I am generating the multiple modes of data from a single data. I have a single video data.
No, you can input the photo and also the text accuracy.
He is asking about the multi-mode of data, like how it is working. He's asking how the Gemini is.
Oh, you're talking about this new model. Unfortunately, I'm not trying to look into that, right? See, there are different types of multi-modal systems. Okay? I can talk about multiple modes like audio, text, and video. Right? So there are 3 different modes on types of data. Right? Then internally in the system, I have one module to process the audio data, one module to process the text data, and one module to process the video data. And then I'll combine that. Right? That's one type of multi-modal system. Another system is I have a single input data and I generate the multiple modes, multiple representations, right? From this single. Like what? Right? Now depends on what.
Is there a multi-model?
Which one? No, see here the task itself involves multiple inputs. Right? Like if I want to perform common sense reasoning, I'm going to have the image, I'm going to have the question, I'm going to have the answer. Right? So I need to combine all these. Okay, but we don't normally refer to this as multi-modal.
And the one now is transfer model.
Yeah.
There is a quantum like layers operations.
Yes.
How many people from the
Layer normalization is basically you're taking the outputs of the nodes layer, right? And then normalize. That's
the multiplication?
actually typically, yeah. Go back. Yeah. See how this 2 different adding stages, right? See, when you are getting, let's say we take a feed forward, right? You have the output of the feed forward. There, you have the output of the nodes in the final data, right? Just do the normalization. Right? This is within the layer normalization. Batch normalization is completely different, right? So where what we are doing is basically right? So basically captures I don't want to details there, right? So basically capture the variances of the nodes layer over the number of examples against batch, right? And capture the little average of the logins. Correct. So that normalization is different. Yeah. So that normalization is normally done to deal with the evaluations. That's one of the solutions. Yes.
Pre-trained and fine-tuning using language models. Pre-training is like if you are using
Take some text data and then go ahead.
there are some like say the consideration of mass language. And also fine-tuning for the downstream task.
For whatever the downstream task you want to use that part of the product, right?
Okay, I'm talking about what they are saying is first the first person. From the second versions and third versions, what they are saying is I will bump up these many layers of the security, and I will only pre-train them. I won't do any fine tuning of the downstream task, but I will ask some questions and give some examples to answer it. They are called one-shot or fine-shot. How it's going to work? It's even performing well when compared to this fine-tuned work models.
Okay, I don't have answer for your question. Okay, because I need to look into details of what they are doing.
Like, what is the main reason for this transform? What's the main it has explored options. What is the main sequence of the even such attention is like from previous models. Attention in LSTM is also
That attention is completely different from the way this is. Yes. Secondly, the LSTM is a model where there is a precision that you do only between the encoder output and the model. Right? So it's a kind of cross attention. But it doesn't use any of this transformation. Right? It uses some kind of similarity, right? And then uses simple. But here, as we've seen, right, the number of transformations is given by the context. Right? So typically, as we go for more number of heads, right? And one important reason why this transform models are successful is mainly because of scope of the calculation and its ability to prove it.
comment that I've seen on the internet. Students at RMS are like a special version of the neural network, whereas transform is like another different neural network. These excels in generalization is more general than where RMS is in. What is
I don't think there is a proof of that. There is no proof, right? Actually, generalization is a very complex topic. Okay, I used to book some what is known as learning and generalization, right? Where they used to formulate the theories for generalization. Okay, just for the people. Generalization. What is generalization?
It's not permissible to anybody to perform well on the test.
Yes, right. So how do you make the model that is being trained on some data to perform well on the data which is not being right? Like all of you know, support vector machines are in principle are supposed to have a very good definition, right? There is not a theory behind that. Unfortunately, there is no theory for the transform models to say that they have a better generalization than the other models.
I have used this data set from IIT for my English translation from English to Telugu.
Right.
What is the effort going on that preparing the data set? That is a big data set containing all the English language, the Chilean language.
What project that we undertaken for that was so where they want to develop a system for one language.
Is it human?
This is what training you need. You need somewhere minimum amount of it, right? So there's a lot of effort that's being put in, collect the data, clean up the data, so on, right? But once you have a minimum amount of data, then you can do some kind of bootstrapping methods, right? To develop the system. Yeah, good. Any other questions?
I have one query. What is pre-trained model? So it has already questions and answers.
No. That has been trained only with the general text data.
It's data.
Yeah.
So for an open-ended question, how can we have a simple answer?
No,
that,
no, no,
the
no.
image
When I
that
say,
we-
see, for any question, normally we expect only one answer to be there. Right? If there are multiple answers, then the question is a kind of ambiguous.
So
Yeah.
that previous slide you were showing, that, in a restaurant.
Hmm. Yeah.
Image was
Oh.
there.
Okay. Yeah, you want to look at that example. Okay. This is the one?
No, this is last, in the last.
Questions.
Oh, okay. Can you go to the last slide? Last button. After this? No, no, there was one question about the common sense reasoning. Yeah, yeah, yeah. That image is in a restaurant. Yeah, yeah, right. Yeah.
How can we analyze that answer was correct? Somebody, if some human, if there were 10 humans interpreting them, there will be different answers.
Good question. See, we are not talking about how these systems are evaluated. All right? Okay. Let's say all of you know how to evaluate a classification model. All right? How do you evaluate a classification model? You have the data, the training data, and also the validation data, right? And you have the desired output for each of the examples in this training and the validation data. Then you look at what are the labels that are given by the model, and then see whether they are matched, right? Now, if I want to evaluate a captioning system, how do I evaluate the captioning system? No, it's not subjective.
Generative metrics, right?
No, that's fine. But I'm asking in general, how do I evaluate a captioning system?
There are
Again, I have set of images for which the ground truth is available, right? Now the system generates a caption. Now I need to match these two captions, system generated caption and the ground truth caption. I need to look at how these two captions are similar. They will not be exact match, right? So there are a number of methods of evaluating this captioning system's performance, right? One of the methods is what is known as the blue scores, right? Where it looks at, if it's a blue 1 score, it looks at simply how many words in the ground truth are matching with the words in the generated caption. In the blue 2 score, we are looking at how many pairs of words are matching and so on. But it's looking at only pairs of words or groups of words, right? It's not really looking at the content of the sentence, right? So there are other scores like Metis score and other scores, right? So you need to come up with a way of evaluating the performance of the systems, right? In the case of the question answering systems, also it is a multiple set of questions, is something similar to the classification task. But if it's an open-ended question answering system, right? So answer is going to be again a sentence. Okay. Now you have the ground truth answer, you have the answer generated by the system. Now I need to see how close is this system generated answer to the ground truth answer, and then come up with the measure of the performance. Yeah.
So you were talking about the non-linearity among the transformers. So the most famous one that's used is Raven. But transformers prefer 10x. Why is that?
Simple. All of you know what is the real is, right? It gives zero output for the negative inputs and non-zero output for the positive inputs, right? So only when the inputs are guaranteed to be non-negative, it's meaningful to use the ReLU.
Variants of ReLU do give some values to.
Yeah, but that's only minor variations. Okay, basically it gives very small output values for the negative inputs, right? See, ReLU has been shown to be very effective only for the CNN models, right? Mainly because you are representing an image. How do you represent the image? It's only color pixels, intensities, right? It's only positive numbers. There are no negative numbers there, right? So that's why the ReLU is very effective there, right? But when you're talking about all the other models, there's no guarantee that the inputs to that model where you're using the ReLU are non-linear, I mean, non-negative, right? Whereas the sigmoidal and the sigmoidal activation functions, right? They are basically designed for the negative as well as the positive inputs, right? That's the reason. Yeah. Now, the reason why the ReLU has been very successful is that it doesn't have the saturating values, right? The positive side of the Rayleigh function, right? It's linear, right? There is no saturating. If you take the sigmoid functions, there is what's called saturating regions. And as all of you know, the gradient is related to the slope of the activation function. So if the slope of the activation function is 0 in the saturating regions, it will slow up the learning process because the gradient is going to be close to 0. That is one of the reasons why this Rayleigh has been very successful in the CNN, right? But otherwise, typically, where you don't have the only the non-negative inputs, right? It's not appropriate to use the Rayleigh function. It's better to use the sigmoid functions. Yeah. Good. Any other questions?
In the interest of time, I think.
Okay.
So,
Yeah. Thank you.
once again, thank you very much, sir, for coming here in person. So, yeah, the talk was very nice. So, let's have the round of applause.
We need to follow it up with the reading of the papers. Of course, there are a huge number of papers, right? Before things evolve.
Still, if you have any doubts, so you can mail him. Yes, sir.